we started talking about particle kinetics. So back to particle kinetics. And the big result of particle kinetics, this is in 2 dimensions, is the equation of motion. Equations of motion relate the causes of motion to the motion itself, to the kinematics. And this is Newton's second law, N2L, I call it. And it says that if you add up all the forces on a body, it's equal to the mass of the body times the acceleration of the body's center of mass. And we've already done an example or two how if all you want to know is the net force, all you want to know is the total force on the body, then calculate the acceleration and that's enough. Usually, though, we don't want to calculate the net force. We want to calculate individual forces. So there might be 5 forces on this object. It's on the ground. Gravity's pulling on it. There's a rope tugging on it or whatever. And we want to know what those individual forces are. For engineering purposes, it makes sense why you would want that. You need to know how strong that cable needs to be, or how likely it is that it's going to break through the ground, or that kind of thing, you know. So if we want to know individual forces, which is normally the case, we need to draw what's called a free body diagram. FBD. Now, anytime you use Newton's second law, you need to draw a free body diagram. And I mean, I remember being in physics 1 and feeling like sometimes there were these rules that were kind of arbitrary, you know, like in these simple problems, even in the more complicated problems we're going to do, it's possible to not do a free body diagram and get the right answer. And when that happens and you get a point off or whatever for not having a free body diagram, it's a frustrating feeling. I understand that. But the reason that you need to draw a free body diagram is not so that you're able to do the kind of problems we're going to do in this class. It's to set you up with good habits for when you start doing more complicated problems as your engineering, you know, time goes on. And so yes, if you get the right answer without a free body diagram or with mistakes in your free body diagram, you'll lose points for that. But the reason is that I consider this to be a very important habit to get into now. So don't forget these. A free body diagram. So what is a free body diagram? The free in free body diagram means the only thing you're drawing is the chosen object. Other objects, other things that are not your chosen piece of a body or collection of bodies or single body that you've chosen to analyze, only appear as forces. So other bodies only appear as the forces they apply to the chosen body. Okay, so that's why it's called a free body diagram. Everything else is out of there. You only have the stuff you're analyzing and the forces that are applied by other things. And here are the steps to drawing a free body diagram. First, draw a closed outline of the chosen body. Okay, so for example, let's say you want to draw a free body diagram of this car I'm going to draw below. So here's the actual nearly photographic image of the car. You might be amazed to see this photograph developing before your eyes. Okay, here's the car. The flag of Italy or whatever. So the free body diagram looks like this. Closed outline. You don't draw the grass. You don't draw the flag. It's just the thing that you're isolating, just your chosen object. So this is what you want to do. What you don't want to do is this or this or this. Okay. And you don't have to, it doesn't have to be artistic. It just needs to be clear to the person looking at it what is considered inside. So basically you're drawing a very clear distinction between what's inside what's in your chosen object and what's out. Okay. What matters is the boundary. Um, so here we know that the wheels are included. We know that the body of the car is included. We know the grass is not included. The flag is not included. It's easy to see. Here, they're internal details. Okay. That can confuse what the boundary is and what's inside the boundary and what's outside. So no internal details. Here the grass is drawn. Is that included, or so you don't want that in there? And this is not a closed outline. Okay, so the whole idea is just to be as clear and simple as possible about what's in and what's out. So no internal details. And no external objects. Okay, so that's the first step. And then the second step is to represent all forces acting on the chosen object. As an arrow pointing in the direction of the force. And a scalar label. So that can be a scalar variable or a number, if you know a number, representing the magnitude of the force. magnitude. Okay, so for the car example, I already drew the outline. So there's the closed outline of the car. What forces are acting on it? There's a weight force. Gravity's pulling down on it. And then the ground is applying forces to the car in two places. There's one here, I'll call that F front. And there's one here, I'll call that F back. And since we're doing two-dimensional analysis, there isn't anything else. You don't have to differentiate between the like left and right wheels in each place. Yep. The weight is always going to be applied at the center of mass of the object. Okay, so how do you know when you've dealt with all the forces on the body? How do you know when you've represented every force? The answer is, and this there'll be cases where you'll look at a problem and there's just so much going on, your brain wants to sort of short circuit, like your brain just wants to kind of put on it. But if you're sort of disciplined about thinking about what types of forces there are, you can get past that. There are only two types of forces that we're going to deal with. The first one is field forces. And in this class, that's essentially just going to be the weight. It's just going to be the force applied by gravity. But there are other possibilities. If you have a charged particle in an electric field, that could fit into this category. If you have a ferromagnetic material in a magnetic field, that can fit into this. This is the one that's going to come up in this class over and over again, just the weight force. And then the second one is, oh, by the way, force fields, like they sound really cool in comic books and stuff, but all a force field means is that the force applied, the force that thing, whatever it is, applies, gravity or the electric field or the magnetic field, is known as long as you know where the object is. So for a weight force, if you take an object with a known mass and put it here, you can calculate what the force is, and it doesn't matter how you got to that position. And so you can think of gravity as a force field. It's the same with electric fields, magnetic fields. It doesn't matter how you get a charged particle to this spot in electric field. If you're at this spot, you can calculate the force. Okay. And then the only other type of forces is contact forces. And these are applied to the boundary of the chosen object by the surroundings. Okay, so let's go back up to this free body diagram of the car. And so even when things get complicated, all you have to do to make sure that you've represented every force that acts on the body is first apply any field forces. For us, that's almost always going to be only gravity. But so there's a weight force coming from the center of mass of the object, going down towards the center of the earth. And then just go around mentally, go around the boundary of the chosen body, looking for places where the surroundings make contact with the boundary. In 2D, that's just following this line around until you get back where you started. So you get to the bottom of the wheel, and there's contact with the grass, so there's a force there. Now, so far, we haven't talked about how to know the direction of that force, but that's what we'll talk about next. And then nothing, 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 and then you get to this one. There's another contact with the grass, so another force, and then nothing else. There's air, so if the wind was strong enough to create a significant air drag, then you'd have to represent that somehow too, but usually air won't appear in there. And so now we go all the way around, get back to where we started, and we know we're done. What about the Italian flag? You know, there's this flag in the picture, but it doesn't make contact with the boundary anywhere, and so there's no force applied. So the next thing we have to know is how do we come up with the directions of the individual forces, the contact forces? So directions of forces. And I'm going to break this up into 5 different types. The first one, the easiest one, is the weight force. That's always just pointing down. But then we also have to think about pushing contact. Pulling contact. Friction. And spring forces. The force applied by springs. And as far as the difference between pushing and pulling, you can think of a pushing contact is resisting 2 objects merging, you know what I mean? So this is the force that keeps them from just like, oh. That's stupid. Pulling contact, you can think of that as like resisting escape. The 2 objects are trying to get away from each other. And so we're going to just go through all these one by one. One more thing about this. There are these very general ones. The first 4 all seem very general. And then the 5th one, I think, when you first see it, is like, well, that's an odd thing to include in this list. Like springs, like how often do you interact with springs in your, like, you know what I mean? Like, why is that such a big deal that it gets its own category along with pushing? You know what I mean? But spring forces are very important in engineering because the way we represent springs mathematically is actually the way we represent a lot of engineering materials. and even a lot of non-engineering materials in specific cases. So like if you apply, so if you take a spring, you know, a coiled spring, and you stretch it out, the spring is going to try to return to its original length. Okay. And so, like, if you stretch it out, it's going to try to pull your hands back together. It turns out that, like, say, steel or engineering materials, if you apply, it has to be a much bigger force for it to be significant. But if you apply a really big force to a piece of steel, it'll stretch a little bit, not very much, you know, but it'll stretch. And that stretch will try to, the steel is going to try to keep returning to its original length. And so it's going to pull your hands back together. And if you let go of it, it's going to return to its original length the way a spring does. So the mathematical treatment that we're going to be dealing with for springs is going to later, grow into the mathematical treatment of engineering materials. Okay. I think that's why it's so important. So you can think of this as elasticity is what this eventually turns into. Um, what does the word elastic mean to you? You know, like elasticity more like a larger force. Well, let me. So when I yes, it's so that's true, but there's a little more to it than that. So it does, and it does deform. And I think you know, before I started thinking about it like mathematically and stuff, I sort of thought of elasticity as things like elastic. What's the elastic in your underoos? You know, um, you all have underoos, I hope. Um, and you think, oh, it's why they stretch. You know, um, and you're right that it provides a resistance to that deformation. It doesn't just flap apart or whatever. What really makes it elastic is not that it stretches when you apply forces to it. It's that when you take the forces away, it goes back to its original. So that's why you put on your underoos and you're like, and then because Play-Doh stretches are like silly putty, but if you made underoo waistbands out of silly putty, you'd go like this, and it would just fall down, and that's not good underwear, you know. So elasticity, the idea of elasticity is if the loads are gone, it's at its resting position. You apply the loads, it deforms, you let go, and it's back at its resting position. Okay. So let's start with weight forces. And the weight force is the force applied by gravity. Um, so this is actually one we can do as kind of a thought experiment. Um, so let's figure out what the force is that's applied to an object. So what's the weight force on an object with a mass m? Okay. Well, the way we can think about it is think about an object with a mass m in free fall. So to figure this out, consider an object with mass m in free fall. Okay, so it could be any kind of free fall or projectile motion. So this object would be following some kind of parabolic path, and it has a mass m. An object in free fall only has gravity acting on it. That's the definition of free fall. So the only force applied is gravity. And so Newton's second law says that if you add up all the forces applied to that object, it's equal to the mass times the acceleration. Okay, so the net force, which is just the weight force in this case, because it's free fall, and that has to be equal to the mass times the acceleration. What's the acceleration of something in free fall? G down. Yep. And so if our coordinate system is like this, then the components are 0, negative 9.81. And so the weight force is equal to 0, negative 9.81 m. Or in other words, mg down. Okay, so this is true all the time. The one with the components is only true for our chosen coordinate system, but this is true no matter what coordinate system you choose. Okay, well, so if it makes sense to you intuitively that gravity pulls exactly the same way on things, whether they're in free fall or whether they're sitting on the ground or no matter what's happening to them, then this is the force applied by gravity all the time. And if that makes sense to you, you're good. If that doesn't make sense to you, I can't really help you, but you did make this make sense to yourself. Okay, so this says is how does your bathroom scale? So your bathroom scale has a setting for pounds and a setting for kilograms. Okay, so one of those is a force, pounds, and one of those is a mass, kilograms. How does your scale, like what is your scale measuring, and how does it know what the other one is? Is it measuring mass or is it measuring force? Well, it's measuring force, but indirectly, it can tell you what your mass is as long as it makes the correct assumption about this constant of proportionality. Okay, so it's easier to think of it as if your scale had a setting for newtons and a setting for kilograms, then what the electronics in your scale are based on the assumption that you're going to be basically on the surface of the Earth. And so the constant of proportionality is going to be 9.81. And so it calculates the force you're applying to the scale. And then it applies that constant of proportionality and tells you what your mass would be. If you took that bathroom scale to the moon and measured yourself, it would tell you correctly what the force is you're applying to the scale, but it would tell you, it would incorrectly guess what your mass is because the constant of proportionality on the moon is different than on Earth. Did you have a question? Okay. Okay, yes. Any other questions? So let's do an example. We can already do some problems this way. Now that we know this about gravity. So let's say that there's a scale on the ground, and person on the scale in underoos. And let's say that the mass of this person is 80 kilograms. What's the force vector applied to the person by the scale? Okay, so I'm going to start out with a free body diagram. So here's the person, closed outline, and there's a weight force going down that's equal to 80 times 9.81. I think that's 78.48. And then for now, we don't know the direction of, we haven't talked about pushing forces yet. It's a pushing force that the scale would apply to the feet. So let's just say the most general we can be about it is, let's say that there's going to be a y component and an x component to this force. Okay. And let's calculate what both of those two components are. Any questions about that?
Right?
Um,
Like in this, for example, diagram, like would be the force of F would be like the y, and force of x would be the front.
well, they're all just acting where the feet make contact with the scale. But we're just saying in 2 dimensions, the most general we can be about the force that's applied to the person by the scale is to say there's an unknown x component and an unknown y component. So that's what we're doing, and we're just going to calculate both of them. If you had to guess, you would probably guess correctly that fx is going to end up being 0. Yep. Oh, 7. Yeah. Trying to be within 1,000% with my estimates. Right number is bad decimal. 784.8. Thank you. And now we can use Newton's second law. So we have, you can think of this as Fx. You know, these are 2 different forces. I'll just write them as a single force with those 2 components. Plus, if we're using our usual coordinate system, this downward force would be 0, negative 784.8. And that's equal to the mass, 80, times the acceleration. What's the acceleration of this person standing on a scale? 0. And so you get that Fx is equal to 0. Fy is equal to positive 784.8 newtons. And so altogether, the force that the scale applies to the person's feet, no, if you do the algebra, add 784.8 to both sides. And so the force applied to the person by the scale is 0 for x, 784.8 for y. Or in other words, you can also think of that as an upward force of 784.8. Okay, does it make sense that the scale is applying an upward force to the person? Yeah, because think about if that force wasn't there, this person would sink into the scale, right? Would free fall into the scale. And so that upward force is required to keep the person from sinking into the scale. Any questions about that? Okay, let's do a similar one, the same person. But now let's say that the scale is on an elevator. And the elevator is accelerating down at, let's say, 2 meters per second squared. Probably shouldn't go in the elevator in your underwear, but that's why it's good to be able to calculate it and you don't have to do the experiment. Okay, so it's the same person, really small elevator. Now what's the force applied to the person by the scale? Anyone have any intuition about how it's going to change or if it's going to change? It would be pretty weird for me to do this problem again if it wasn't going to change. It's going to measure a smaller weight. Yeah, that's right. If you stand on a scale in an elevator, when it's going down, that doesn't mean that it's accelerating. But for that brief period where it is going from rest to getting up to speed going down, you would see the weight on the scale drop. Okay. So let's see mathematically why that works. So again, we have draw a free body diagram. We have the weight force of 784.8. And then again, I'm going to say we could have an X and a Y component. Later on in problems like this, we'll know what the direction is before we go into it. But for now, let's be general about it. And now Newton's second law says force applied by the scale, Fx, Fy, plus the weight force of 0, negative 784.8. So your weight doesn't really change because you're accelerating. What changes is just the force that the scale applies to your feet. Gravity still pulls the same. Equal to the mass times the acceleration of the person. And what's the acceleration of the person this time? 0, negative 2. Yep. With the elevator, the person's accelerating down at 2 meters per second squared. And so again, we don't have any horizontal stuff going on, so there's no x component to the force. But the y component is equal to 784.8 minus 80 times 2, so minus 160. And so you get a value of 624.8 newtons. And so the force applied to the person by the scale is 0, positive 624.8 newtons, or that means an upward force with a magnitude of 624.8 newtons. Um, how much acceleration downward? So if the contact force applied by the scale keeps going down as you accelerate more and more, what do you think? Where do you think the amount of acceleration downward is where the person's weight would be 0? 9.81 down. Yep. And then that's like the vomit comet thing that we talked about. If your surroundings are accelerating with free fall acceleration and you're accelerating with free fall acceleration, you have apparent weightlessness. If you switched it around and made it a positive acceleration, you could look through the math and see how that would work, and it would look like your weight was increasing while you were accelerating upwards. And that's why you feel like, do we ever have this experience? If you're accelerating upward, I guess you feel it in an elevator, that you feel slightly heavier until it gets to a constant velocity, and then that feeling goes away. Yeah, that's right. Yep, you're sort of pinned into your seat. Any questions about that? Um, Let me do pushing really quick. So when two objects are in pushing contact with each other, so the contact force between them is keeping them from merging. Are in contact force. That's the whole key here. With each other. The force on the chosen object is perpendicular to the surface of contact and toward the chosen body. Okay, so for example, let's say that on the floor there's a box. Call that body 1, and then it's leaning against, oh, I missed. It's leaning against a ball. I'll call that body 2. Then a free body diagram of the box, body 1. There'd be the weight force. I'll say M1 is the mass of the box, so M1G going down, that's the weight force. And then there'd be a pushing force applied by the ground that's perpendicular to the ground toward the box. Excuse me. So I'll call that N1 for, just that's just a variable name, but the N stands for normal force. So I'll use that capital N as a variable a lot. And when I'm using it for normal force, I'll always put the fancy patent shoes on it like that to differentiate from the units of newtons. Okay. And then there's also a pushing force between the box and the ball. And so that force has to be perpendicular to the surface of contact. So it's going to be horizontal and toward the box. And I'll call that, again, it's just a variable name, but I'll call it R for reaction force. And now let me draw the free body diagram of the ball too. So there's a weight force, the mass of the ball times G. The ground and the ball are pushing on each other. There's that force preventing the ball from sinking into the ground. And so that's an upward force. And the variable I'll use is, I'll call that N2 for the normal force on body 2. And then since the box and the ball are pushing on each other, the force has to be perpendicular to the surface, so it has to be horizontal again, and it has to be toward the ball, so this way. And here's something I didn't talk about, but it's true, and we'll talk about why it is later on. The magnitude of those two things has to be the same. Even if they are moving, it has to be the same. That's called Newton's third law, and we'll talk about it more later. But that's going to be a really key idea. So if you have two things that are in contact, the force one applies to this one is opposite direction and equal magnitude to the force this one applies to this one. Your test, I'll get you back tomorrow. Yeah, the lab test, and yours, and someone else, one more person. I don't think it is yet, but it will be by this afternoon.